Hey everybody. I wanted to talk a little bit about what we spoke about in class recently, which was all things atoms in the periodic table. The structure of atoms, how they're organized in a model that might predict how they behave, and how that relates to what the periodic table looks like and their position on the periodic table. You may have heard about some of this before from a previous class. It might be a refresher for some, but it's always good to start with a basic thing to get us all on board with what we're going to be doing in this class and how we're going to be using and referencing the periodic table throughout, and probably in Bio 102 as well if you go on to that. Because this is a biology class, we talk a lot about carbon. So I'm going to be using carbon as the reference atom or the reference element for this conversation. And if you look at carbon on the periodic table, you might have one in front of you, or you remember one from class. You can always Google one and pull one up. Carbon is atomic element number 6. So I'll draw what you might see if you looked on a periodic table. Here's the C for carbon. It has an atomic number of 6, so there's going to be a 6 on there somewhere. And it has an atomic mass of 12.011. So when you look at a periodic table that is reasonably complete, you'll see at least that. Sometimes it'll actually say carbon on it or something like that, but not always. Sometimes in the sleeker versions of it, it'll just kind of leave the actual name out and leave you to infer, which is fine. So the 6 at the top, like I said, represents the atomic number, which equals the number of protons. What this means is that if you change the number of protons, which we can find in the nucleus, you're not just doing something with the mass. If you change the number of protons, you're actually changing the element that you're referring to. If the atomic number is 6 and we have 6 protons, then we're talking about carbon. If the atomic number is 7 and we have 7 protons, we're not just talking about a heavy carbon. Now we're talking about a different element entirely. We're talking about nitrogen. So like I said, we're going to stick to 6 on here. We're going to stick to carbon, most of what we're going to talk about today, because that is the one that we think about most often in association with biology. But there's a lot of other elements that we talk about in biology as well. Let's start here. This number on the bottom is the atomic mass. And then is the number of protons plus the number of neutrons. Why is it a decimal? It is a decimal because it doesn't just represent a fixed number of things that there's only one kind of carbon in the universe. There are 3 different versions of carbon out there. There's carbon 12, which has 6 protons and 6 neutrons. There's carbon 13, 6 protons because carbon always has 6 protons and 7 neutrons. And carbon 14, which has 6 protons and 8 neutrons. Like I said in class, about 97% of the carbon that is out there is carbon 12. About 2% is carbon 13, and about 1% is carbon 14. If you take the weighted average, that's the kind of average that you take when you do your GPA, 12.01 grams per mole. And the mole is at 6.02 times 10 to the 23rd. So 6.02 times 10 to the 23rd atoms of carbon will weigh 12.01 grams. That sound good? Awesome. I'm going to give this a quick erase. Hopefully a quick erase. I want to talk a little bit about what this means in terms of how carbon is organized in space. So if we actually wanted to draw a carbon atom, we would start in the middle with the nucleus. So the nucleus has both protons and neutrons in it. So we know that there's going to be 6 protons here. If we think about the neutrons that are in there, they're a lot like a proton. They carry about a similar amount of weight. They add to the mass, but they don't add to charge or anything like that. We're going to go with like the usual kind of standard, most common carbon, which is carbon 12. So if we're going with carbon 12 and we have 6 protons, that means we also have 6 neutrons in that nucleus as well. How are the electrons organized around this? I like yellow for electrons because it seems nice and energized to me. We put them in what are referred to as shells. So here is the innermost shell of electrons. We can think of that as where the electrons that are going to be interacting with things around it might live. And we're going to have to put 6 electrons on here to make this electrically neutral. So we're going to shoot for 6. I'm going to write this up here just so I remember. We're going to have 6. I'm going to make it so people can actually see it. We're going to have 6. There we go. 6 electrons. So I'm going to put 1 here, and I'm going to put 1 there. I usually refer to my electrons in these models like this as X's. So when you see an X in a dotted line that goes around a nucleus, that's an electron. 2 down, 4 to go. We can have another layer of electrons around that we can put those extra 4 in. This inner one, this inner shell, can only hold two electrons. So I need 6 more, I need 4 more to go, so I'll go 1, 2, 3, 4. This outer shell can hold a total of 8 electrons, but we don't have 8 electrons to spare. We only have the 4 that's left over. So there are going to be some vacancies in here where electrons can go, which is cool because when you have vacant spaces where more electrons could go in this outer shell, that is where you can make bonds. That's where you can make covalent bonds, where we share electrons with something else. And we'll talk more about that in some content coming up soon. But for now, this is how you would draw an atom of carbon for the purposes of this class, and probably in Bio 102 as well. Eventually, we're going to start being a little more fast and loose with how we draw it. And when we draw larger molecules, we won't always draw every electron. We might just draw, like individuals put a carbon bonded to a carbon, bonded to another carbon, 3 carbons in a row. But before we get to this kind of structure of how we can draw molecules, we want to make sure that we know what's going on and we understand what's going on in the actual atom itself. Because this structure of how many shells there are and how many electrons there are in each shell is going to be something that is going to predict the behavior of our larger molecules and what they can do. So I hope that this video was clarifying a little bit on what the periodic table represents in terms of what the little squares mean and how atoms sort of going to be drawn that model their behavior as they exist in biology classes and where we might be going from here. So I hope you enjoyed it. Let me know if you have any questions. I'll see you guys soon.